Today's lesson is called Related Rates. We are going to differentiate each of these formulas with respect to time. This is kind of like implicit differentiation from earlier this semester. Whenever we take a derivative of a variable that is not time, which is not a variable in any of these equations, it will generate its own rate. So let me show you how this works. We'll start with number 2 here. The volume equals pi r squared times the height. This is a formula for volume of a cylinder. So you would have to use the product rule to take the derivative of this. Pi r squared would be the first function, and h would be the second function. Each variable is kind of like its own function here. Pi, of course, remember, is a constant, not a variable. So the derivative of the volume with respect to time is going to equal, I'm going to take my first function, pi r squared, using the product rule here, times the derivative of the second function. What's the derivative of h with respect to time? dh, oops, that's an h, dt, plus the second function, which is h, times the derivative of the first function. And what's the derivative of pi r squared with respect to time? Well, use the power rule. 2 times pi times r to the first power times the derivative of r with respect to time. dr dt. The important thing to remember here is that every variable generates a rate. Okay, so number 4 is like a super easy one. The derivative of the area with respect to time, this is the area of a square formula, would be 2s ds dt. Every variable should have one of these rates for it in the problem somewhere. Let's do number 3 and then we'll move on. This is the Pythagorean theorem. So I'm going to take the derivative of a squared, which would be 2a, then dA dt, that variable generates a rate, plus 2b dB dt equals 2c dC dt. Okay, hopefully you're kind of understanding that general mechanics there now. So let's do some examples here. Number 2, and I'm going to have the answers to all of the notes problems at the end, but we're just going to do selected ones here. The width of a rectangle is increasing at a rate of 2 centimeters per second. Okay, so here's a given rate. And its length is increasing at a rate of 3 centimeters per second. So this is another rate. At what rate is the area of the rectangle increasing when its width is 4 centimeters and its length is 5 centimeters? Whenever you read the word when in one of these problems, that is giving you data that it's not constant, it's changing data, and you'll plug that in after differentiating. You cannot plug it in before or you'll end up in a bad situation that you will not get the answer to the problem. So watch for that word when. It's really an important word in these problems. So we have a rectangle here. The width is increasing and the length is increasing. We need a formula that relates the variables in the problem. This would be area equals length times width for a rectangle. And we're given rates. dW dt is 2 centimeters per second. dL dt is 3 centimeters per second. So are any of these constant in the problem? The area, the length, or the width? No. Everything's changing. The length is changing, the width is changing, the area is changing. So I can't plug in anything until after I've taken the derivative. So dA dt, the derivative of the area with respect to time, is going to be equal to, this is a product rule, L times W. So I take the first function, which is L, times the derivative of the second function, dW dt, with respect to time, plus second function, W, times the first function, dL dt. So, now that I've taken the derivative, it's perfectly fine for me to plug stuff in. So I'm looking for dA dt. What rate is the area of the rectangle increasing? So this is what I'm trying to solve for. When the length, what do I plug in for length? 5. And then dW dt, that's 2, plus the width is 4, and dL dt is 3. So this is going to give me dA dt equals 22 centimeters squared per second. Okay, these rates were both given in centimeters per second, and area would be centimeters squared per second. Alright, next one. We're going to do number 4. A man 6 feet tall is walking away from a spotlight, L, located on the ground. His shadow is cast on a wall 40 feet from the spotlight. If the man is walking at a rate of 4 feet per second away from the spotlight, determine the rate of change of the shadow, PQ, when he is halfway to the wall. Okay, so what do we know here? The man is standing at A. He is 6 feet tall. That's given. He's walking away from the spotlight, so he's walking in this direction. His shadow is over here. Shadow. And that is 40 feet from the spotlight. We have a rate that he is walking at. So let's see. 4 feet per second. So, and we're supposed to determine the rate of change of the shadow, PQ. Alright. So ds dt is what we're trying to find. He's going this direction, so I'm going to call that along the x-axis, dx dt equals 4. That's his rate. Now, there is a piece of when information here in the problem. No, just kidding. Okay, so what relates the variables in this problem? There are a pair of similar triangles. If you'll look, here's a small right triangle, and then here's a large right triangle. Those are similar to each other, so we can set up a proportion as our formula for this problem. We're going to say x is how far he is away from the light. So his distance from the light over his height, 6, would be equal to the distance the shadow is from the light, which is 40. That's a constant. It's not changing. So we can go ahead and plug that in before differentiating, over the height of the shadow, which is a variable. That's an s, not a 5. So this gives us the formula if we cross multiply, the way we solve proportions. X times s equals 240. So that's a product. We're going to take the derivative of it, first function, times the derivative of the second function. plus second function times the derivative of the first function, and that's going to be equal to the derivative of 240, which is 0. So, now I'm going to plug in what I know. We've got the x. What is x? What is the distance that the man is from the light? Well, it says when he is halfway to the wall. So if he's halfway to the wall, that means x would be 20. So I have 20 times ds dt, which is what I'm trying to find, plus, what would that make s be? 20s equals 240, divide by 20 on both sides, s equals 12. 12 times dx dt is 4, equals 0. So, this is 48. So if I subtract that 48 from both sides, 20 ds dt equals negative 48. Divide by 20 on both sides, ds dt equals negative 48 over 20, which simplifies to negative 12/5. And that would be in feet per second. Okay. Example 6. An airplane at point A is flying 600 miles per hour on a horizontal path that will take it directly over an observer at point O. So it's going this way, and we are given, I'm going to use an x since that's horizontal movement, dx dt is equal to 600. Now the only thing here is, that's not the positive x direction, that's the negative x direction. So we actually do have to call that negative 600 miles per hour. That direction does matter with our rate, because this distance x at the bottom is going to be decreasing as A gets closer to O. The airplane maintains a constant altitude of 7 miles. So this 7 is a constant. It's not going to change in the problem. What is the rate of change of the distance between the observer and the airplane? So that's talking about the rate of change of z. So dz dt is what we're trying to find. When x equals 5 miles. That is a changing variable. We cannot plug that information in until after we have taken the derivative. Now, what equation relates the three sides of this triangle? Pythagorean theorem. So that would be x squared plus 7 squared equals z squared, which means x squared plus 49 equals z squared. Now, I'm going to take the derivative. That's going to be 2x dx dt plus 49, that's plus 0, equals 2z dz dt. Okay, now what do I know here? 2 times, I can plug in my 5 for my x now because I've already taken the derivative. And then dx dt is negative 600. 2 times, do I know z? No, but I can solve for it. When x equals 5, this would be 5 squared plus 7 squared equals z squared. So that's 25 plus 49, which would be 74, equals z squared. Take the square root on both sides. Square root of 74 equals z. So this would be square root of 74, and then dz dt, which is what I'm trying to solve for. So over here on the left, 10, 2 times 5 is 10, times negative 600 would be negative 6,000. And, dz dt. This is supposed to be a 74 underneath that root, sorry. Now if you divide both sides by 2, you get negative 3,000, and then divide by square root of 74 over the square root of 74 equals dz dt. Now as far as the answer for this goes, I mean, you could rationalize that by multiplying by the square root of 74 over the square root of 74. This actually was a calculator problem, so we would round to 3 decimal places. Negative 348.743. And I would say on most of these problems you need to be trying to do them without a calculator, if at all possible, because these types of problems could appear on the calculator or non-calculator portion of a test, of course, like everything in calculus. So that's the answer, and we'll move on to the next example. Example 8. A spherical balloon is inflated so that its volume is increasing at the rate of 3 cubic feet per minute. How fast is the diameter of the balloon increasing when the radius is 1 foot? So the question is, how fast is the diameter of the balloon increasing? So that's going to be the derivative of the diameter with respect to time. That's what we're trying to find. This when information, when the radius is 1 foot. Now, let's see, what else? Oh, they give us this rate. This is the rate of change of the volume. So dV dt is equal to 3 cubic feet per minute. So what is the formula for volume of a sphere? Well, do you remember your geometry? Volume equals 4/3 pi r cubed. So the only thing is, if I want to find dd dt, do I have a d in this problem? No. How am I going to get a rate that has to do a d if I don't even have a d in my equation? It's not going to work out really well. So I need to change this r to something in terms of d. Well, we know that 2 radius equal 1 diameter. So if I want to replace r with something in terms of d, I could multiply by 1/2 on both sides. R equals 1/2 d. And put that in place of r. R is 1/2 d. Okay, and then I want to go ahead and cube both of those, the 1/2 and the d, to simplify this a little bit. So that's going to be 4/3 pi, what is 1/2 cubed? 1/8 d cubed. And now I'm going to go ahead and multiply those fractions. So that's going to be 4 over 24, which is 1/6 pi d cubed. Now I'm ready to take the derivative. Now notice 1/6 is a constant, pi is a constant, d is a variable. So this is not a product rule situation. We're just going to take the derivative right now. dv dt equals 3 times 1/6 is 3/6, which simplifies to 1/2 pi. Take 1 away from the power. d squared, times the derivative of the diameter with respect to time. So, here's my formula that I'm working with. Plug in what I know. dv dt was given. It is 3. So 3 equals 1/2 pi times, okay, d. Do I have a number for d? Well, I have a number for when the radius is 1. So if the radius is 1, what does that make the diameter? Well, 2 times the radius is the diameter, so it would be 2. So 2 for the diameter squared d dt, which is what I'm trying to solve for here. So this means 3 equals 1/2 of 4. 1/2 of 4 would be 2 pi d dt. Divide by 2 pi on both sides. 3 over 2 pi equals d dt. And the units here would be feet per minute, because we have cubic feet per minute for the volume's rate of change. So the diameter would just be changing feet per minute. And that's the answer. This is a non-calculator problem, so we just leave it like that. Okay? Now, we skipped a few problems on the examples. Let's take a look at those. And I'm sorry that this print is small. Hopefully you can make it a little bit bigger on your screen, zoom in or whatever. Number 1, we skipped. We had a 17-foot ladder leaning against a wall. If its bottom is pulled away at a constant rate of 0.5 feet per second, determine each of the following. And basically, they're just changing the height that the ladder is up the wall in each case. The Pythagorean theorem relates the variables in this problem. 17 is a constant because the length of the ladder is not changing. So we set up the Pythagorean theorem equal to 17 squared. Take the derivative and then plug in the information that we know to get our solutions here. And again, I would encourage you to pause the video, try the problem, and then check your work against mine. So the speed at which the ladder is moving down is increasing as the top of the ladder gets closer to the floor. Alright, then we did number 2. Number 3 is a police car problem. A police car is approaching a right-angled intersection from the north. So the police car is like A, and it's chasing a speeding car that has turned the corner, is moving straight east, so that's B on the picture here. When the police car is 0.6 miles north of the intersection and the car is 0.8 miles to the east, the police determine with a radar gun that the distance between them and the car is increasing at 20 miles per hour. So that 20 miles per hour is dc dt. If the police car is moving at 60 miles per hour at the instant of the measurement, what is the speed of the car? So this is actually the type of calculus that is done to determine speeds of vehicles using radar technology. So this kind of gives you a little bit of insight of the calculus that's involved in those pieces of equipment that are used by police. So these 3 variables are related by the Pythagorean theorem, and everything is changing. The police car's distance is changing, and the speeding car's distance is changing, the distance between them is changing, so we can't plug in anything before taking the derivative here. So this is just going to be the derivative formula that we use here. And then we can plug in what we know. dc dt is 20, so that goes here. Then when, the when information in the problem, 0.6 miles north is the police car, so that can go here. And then 0.8 miles east is the speeding car's distance, and you can use that to find the c, which comes out to 2. So we plug, 1. So it comes out to 1. So that goes here. Here's the 1. Oops, if I could get this thing to write. This is 0.8, this is 0.6, and then we have the 60. Now the 60 we have to make negative because the distance, this distance A is decreasing as the police car gets closer to the origin. So we put in a negative 60. And now we've got everything we need to solve this problem except for dB dt, which is what they're asking us to find, the speed of that car, which is 70 miles per hour. Probably not a good speed to be going as you're turning an intersection. So, next problem. We did 4. Here's number 5. Number 5 is a little bit challenging because the volume of the cone problems, they just tend to be. Water runs into a conical tank at the rate of 9 cubic feet per minute. So the volume of water is changing at a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet. So that 10 is constant and a base radius of 5 feet. So this radius is 5 up here. Ooh, this thing's not drawing very well. How fast is the water level rising? So we're trying to find dH dt, the height of the water. How fast is that changing? When the water is 6 feet deep. So when h equals 6. Now, the formula for volume of a cone is 1/3 pi r squared, which is the area of the circle, times the height. So, the only problem with this is we have v, r, and h. Those are our 3 variables. V we need because we have a dV dt, and h we need because we're trying to find dH dt, but there's no information given about dr dt. So I don't want to use the r in the problem. I want to change it to an h so that I only have 2 variables, h and v. So the way that I do that is I set up a proportion because we have similar triangles going on here. We have the 5 with the 10 on the big triangle, and then there's this littler triangle which has the changing r and the changing h. So if I set up the r over h equals 5 over 10 and cross multiply, 10r equals 5h, divide by 10 on both sides, r equals 1/2 h. And I can plug that in to the formula in place of the r. Once I do that, I square both of those, so I have a 1/4. I combine my like terms. 1/3 times 1/4 is 1/12. H squared times h is h cubed. And then I can take the derivative from there. Okay, and plug in what I know, which, how did I get the 6 for the height? Well, when h is 6, that was given in the problem, and the 9 was given, and then I can solve for dH dt, which comes out to 1 over pi. So the main thing here was figuring out that you needed to get the radius in terms of height so you don't have so many variables. Last one, number 7. This one involves a little bit of trig. A 10-foot plank is leaning against a wall. If at a certain instant the bottom of the plank is 2 feet from the wall and is being pushed toward the wall at a rate of 6 inches per second, how fast is the acute angle that the plank makes with the ground increasing? So I'm trying to find the theta dt when x is 2. And I'm given the diameter. So if you'll remember from your trig, SOHCAHTOA, the adjacent side, which is x, and the hypotenuse means we're using the cosine. So cosine of theta equals x over 10, and then you have to take the derivative of both sides and plug in what you know. All right, good luck with your related rates assignment.